So it's a little bit out of date, but we started thinking about search and motion plan. Today we're going to start covering an idea called heuristic search, right? And so we'll cover algorithms Astar, best first search Dijkstra's, and lazy Astar, which will be things that are on your homework. And then on Friday we'll try to cover RT and RT star really quickly. Yeah. So some logistics. Homework 3 is due today. There was a bit of confusion about, not confusion, but some people weren't able to finish things on time. So we have a slightly different policy that we can submit a video by end of day for credit if you weren't able to come to the office hours, just to give everyone a chance. If you can make it. And if you are not able to finish by today, you can submit by Monday with a penalty. Right, so it's fair to everyone who submits on time, but if you're not able to finish by today, submit by Monday with a small penalty. And that seems like a fair policy to me. Does anyone have objections to that? Seems okay. Paper commentaries are due today. Yeah, they don't have to be deep or profound or long, just some comments would be useful. And we on Friday, one of the groups wasn't able to present. So what we'll do is I will do half the lecture on RT and RT stuff. And then we'll have one presentation from the Steve Speed on RT Connect. And then we won't have lecture on Monday because of the presidents. And we will do imitation learning. We'll start machine learning on Wednesday. And you have a guest lecture from some people at TRI on Friday. Which is on Zoom. So would you prefer that we do Zoom here and everyone watches it? Do you prefer that we do Zoom at home? Like what's easier? They're in Boston, so they're definitely not here. Does anyone have preferences? Zoom here? Okay, yeah, we can do Zoom here and whoever wants to join the Boston. Cool. Any other logistics things that we should bring up? Yeah.
How much is like
I haven't decided exactly yet, but it would be like from a 4.0 to like a 3.98 or something, which is minimal. 3.95, small. But yeah, I'll make sure that I just want to make sure the policy is consistent because I just heard about this. So give me like 2 more hours and I'll email everyone with the right numbers. Okay. Cool. So this is the structure of the class today. We'll start talking about best first search as a class of methods. We'll instantiate a particular instance of best first search for A-star search. And then we'll describe how to make A-star search cheaper with this class of methods called laziness. Okay. How many of you all are familiar with these methods already? Some? Okay. So we'll go through them and ask some questions along with it. So hopefully it's interesting for everyone. So we talked about motion planning, hard continuous problem. You want to get from here to here in configuration space while avoiding obstacles. And we're going to do it by constructing a graph with vertices and edges and trying to do surface of the graph, right? So last time we discussed a number of ways to take this continuous motion planning problem and try to convert it into a graph search problem, right? So we talked about doing things with sampling, and sampling will give you the vertices. And then we talked about doing collision checking to figure out which edges are connected and not connected. Right? And so the assumption we're going to make in today's lecture is that the graph has been constructed. So you've done the sampling, you've done the collision checking, the graph exists, and now you want to figure out how to go from your start to your goal while avoiding all the collisions. And so one important thing to note is that we're going to assume that all the edges in the graph are collision free. So you've done collision checking and you've eliminated any edges that explicitly give you collisions, right? And so everything is collision free. You just need to find the shortest path from the start to the goal. And the shortest path can be either just number of edges, or you can have things like distances or costs associated with each edge. So you want to find the minimum cost path from the start to the goal while avoiding all obstacles. So that's the premise of what we're going to do today. And so we're going to try and find efficient ways to do so. So sampling-based motion planning, we created a graph. Now we want to search the graph. Today's methods are going to keep the graph fixed, but the RT methods we'll cover on Friday, we'll try to keep changing the graph. Okay, so the general search problem, you have a start and a goal, which are both nodes in your graph. you have some cost that is given to you, for instance, edge length or other things like smoothness or jerk. You might have different parameters along your cost, but that is given to you as part of the problem. And then you're given a graph with vertices and edges. And your goal is to find an optimal path. You want to find this optimal path as quickly as possible, right? So in an industrial application, you want to do planning ASAP so that you can like deploy things in real time. So the goal is to find the shortest path or the minimum cost path with as few node expansions as possible, right? And so really what we do in search is we have a graph and we try to like open up different nodes like this until we like find a path that goes from the start. Right? And so typically you have like we call this, you can think of this like a wave front, right? Which is just like you started somewhere, then you like open nodes in the graph until you find a collision-free path to the goal. And you want to do it in a way that that path is the shortest possible path. Right? So for instance, this path you can see is not the shortest possible path. And this path is going to be the shortest path, but this is going to be faster than this. Right, so like for instance, algorithm like weighted Astar will give you a suboptimal path. You can see that it like goes in and comes up, but it'll do it faster, right? And so typically in search, the trade-off is really between optimality and speed. So that's the trade-off you want. Okay, so really what we want to do is we want to search the reason over the space of paths, right? You want to find the shortest path, and you want to do it quickly. And so you want to minimize the planning effort. And so the first part of the lecture, we'll talk about how to minimize the planning effort in terms of node expansions. And the second part, we'll try to think about minimizing planning effort in terms of computational speed. Right. So unlike control, you don't care about continuous things anymore. Now that you live in discrete world, you're just in discrete world, right? You're trying to do discrete search. You're not going to do continuous control, no gradients, no noise, nothing like that. It's in the graph. You plan for the graph and then you let control take care of all the noise, right? So the nice part of our system design is that we have state estimation with the probabilistic estimation. We have control that deals with noise, but planning, you can just do it deterministically. That's not the only way to do planning. You can also do planning under uncertainty, but for today's class, we're just going to do planning deterministically. Yeah. Okay. So the idea we're going to use is this meta algorithm called best first search. When I say meta algorithm, it's a class of algorithms. Right. So a meta algorithm best first search is essentially maintaining a priority queue over a set of promising nodes, right? And each node has a priority of F. You're going to initially just start with your initial node, and you want to, do search by expanding the most promising node according to its priority function F until you reach the goal. Right? And so the best first search meta algorithm is going to essentially keep a list of different nodes, right? Node identities. So in this case, each node is going to correspond to a point in configuration space, right? In your discrete sample set. And then you're going to have some priority F. And the priority F is going to tell you which node to expand next. And by expand next is you want to check if that thing is the goal and look at its successors. Okay, so the general meta algorithm of best first search is something like this. And the design choices you really want to make are like, what is F? How do you populate the queue? How do you open nodes? Things like that. So let's kind of try and think about this more concretely. You want to keep expanding nodes in the graph until you find a node which is like the goal or closest to the goal. And you want to terminate when you find the goal, right? So you want to like start from this thing, expand something, let's say expand A, then you find nodes C and D, you want to add them to your priority queue with some priority S, find the minimum cost thing or like the highest priority thing according to F, open it, expand its successors, repeat. Yes. So let's kind of like look through the pseudocode a little bit, right? So in a best first search problem, you have a starting node S start, a goal S goal, you have a cost function, and you have a graph, right? And what you're going to do is you want to create an open priority queue, which is just a queue of different nodes, right? And they're like priority according to some function. And we'll define what the function is going to be. Along with an open queue, you want to keep a closed list. So just a list of nodes that have already been closed. You don't need to care about them anymore. And then you need to have a function G, or like a table G of S, which is going to be an estimate, your best estimate of the least cost from the start to a given, right? And so open is a priority queue, close is a list of closed nodes, G of S is an estimate, your current best estimate of the least cost from the start to a given. Right? And so you really want to find the path which has the lowest G of S. And everything that goes into your priority queue is going to have some priority F. Right? So there's two functions to remember. F is going to be how you put things in the priority queue, and G is going to be an estimate of the shortest path, your current best estimate of the shortest path from the start to any node S. Right? And those are the data structures we're going to create. And you want to get from start to goal, minimizing costs while opening as few nodes as possible. Yeah. You want to me? Questions? So just to make sure I recap, we are solving a best first search problem. You're trying to like find a wavefront that expands like this from a start to a goal. You're doing this by populating a priority queue. Priority queue has different nodes, which are different states or configurations. Each of them has a priority value. You want to open things according to the priority value, so that you find a path that takes you from the start to the goal with minimum cost. You have questions?
What's the difference between the cost and the priority?
It's a good question, right? So the cost is going to tell you what is our estimate of the sum of edge costs from the start to the current thing under the best possible path you know so far, right? And one choice of priority is just the cost. Like you open the like lowest cost, right? That's going to be the first algorithm that we use. The problem with doing that, it has no notion of how close something is to the goal. So for instance, something might be close to the start. Like here's an example, right? You start here, yeah, and there's like the goal is here, and then you have some node A here, right? And let's say you have another node B here, right? So B is closer to S than A is, but B is further away from the goal, so it's less useful, right? So you might want to, what we're going to try and do is we're going to choose, you want to have a priority that doesn't just take into account the distance, but also takes into account the distance. That's what it means. Okay, so that's going to be the data structure that we're going to create, and that's going to be our notation, right? So the general best first search pseudocode looks something like this, right? You start by just taking the start node, putting into your priority queue, right? And then while the goal is not expanded, like while you haven't like actually reached the goal, you're going to take the best node from open, right? So you have an open list, you're going to take the best node according to your priority F. You're going to check if that best node was the goal or not. Right? And then if it's not the goal, you add it to closed. And for every successor of that node best, you're going to check if the cost through best, so it's G of best plus the cost from best to S prime is less than the current best estimate of G of S prime. Basically it's a better path than you have so far, right? Then you're going to update G of S prime so that it now goes to G. Right? So essentially you can think of it this way. It's like if you imagine you had a path that goes through A this way, right? And that was your current G of S prime, but now you found a different path which is lower cost, right? You want to replace G of S prime in the table by the lower cost path. And so in best first search, you typically want to do something like this, right? And you say if something is like a lower cost path, then you want to add it into your priority queue, or like add it into your open path, so it's a candidate for opening next, right? Like basically, there's a few design choices we make here, right? The first is that we only do these things if it's a shorter path, because you don't care about paths that are longer paths, right? So if I already have a shorter path, if G of S prime is less than G of S plus C of S prime, then I just don't care about S. I don't care about the current node that I bought, right? Because it's just like higher cost, who cares? And once you like have updated something to be lower cost, then you add the updated successor to the open list because it's a candidate to open list. Right? So to kind of recap the algorithm, we start in the priority queue, you pause the best thing from the priority queue, check if it's the goal. If it's not the goal, for every successor, you check if the cost to those successors through that path is shorter than the current best estimate for G of S prime. If it is, you replace the best estimate with a shorter distance and add that to the set of nodes that you can open. And we'll go through this like with a concrete example, right? But intuitively, you just want to like you basically want to keep opening nodes. Like you open some node A, right? And at that point, you want to like check its successors, right? You want to check B and C and D, right? And you want to check for B, if you take the path, the best possible path through A so far, and then you add B, is it shorter than my current estimate to B, right? And if it is, then I want to replace the best estimate to B by the path to A. And I want to add B to the set of things that I should have open. Right? So that's kind of the equation, and we'll go through like the concrete example. Does that make sense? Okay. So like Leo was just saying, the first and simplest thing to do is set the priority F to just the best estimate of cost, right? So you push nodes into the queue with the best estimate of cost, right? So you set F to G, so you sort nodes by their cost to come. By cost to come, you mean cost from the start to the current node. Cost to go means cost from the node to the goal. Right? So whenever you see cost to come, that means from start to A, and cost to go means A to go. Right? And so you sort nodes by their best estimate of cost to come, and you open the most promising things. You open the thing that is like cheapest. And so you can see how the wavefront expands. It's basically expanding in like a uniform way. Right? So because it's always going to pick the cheapest thing amongst the set of candidates that it has. So it's never going to go in like one direction more. It's just going to like expand uniformly in all directions. And so this algorithm is often called uniform cost search or Dijkstra's algorithm, right? But it's trying to find the shortest path to start with the goal, but it expands uniformly in all directions. And so looking at a concrete example, imagine you have a graph like this, right? This is your start, this is your goal, those are your edge costs, right? And so what you'll have is that your G's are going to be something like this. Your cost to come at the start will be 0, cost to come at S2 will be 1, cost to come at S4 will be 1 plus 1, which is 2. Right, cost to come at S3 will be 1 plus 1 plus 3, which is 5. Right, and so the way that the algorithm will proceed is it'll start by putting in Astar, adding in its successor S2. Right, then it'll have S2 in here. It's not the goal. It'll add in its two successors. Right, so now you're going to have S4 and S1 in the queue, and then S4 is going to have cost 3, and S1 is going to have cost 3, and S4 is going to have cost 2. Right, and then you will pick the most promising ones. You'll pick S4, then you add a successor and repeat. So let me see. I think I should have. Maybe I actually don't have an expansion. So let's go through the expansion slowly, so that everyone's on the same page. We start by having S start in the priority queue. So like if I start in the priority queue with like the F set to 0. Right, you'll remove that, and then you'll add in S2 to the priority queue with F set to 1, right? And then you will remove that from the priority queue, and then you'll have S4 and S1 in the priority queue. So S4 will have 1 plus 1, 2. S1 will have 1 plus 2, 3, right? And you pick the lowest one here. So you remove S4, then you add in S3. Right, then you have 1 plus 1 plus 3, so S3 will have 5. Right, we pick the lowest one, S1, and then you have S goal. S goal will have 1 plus 2 plus 2, 5. Right, and then you will pick S goal, and you'll be done, right? And so you'll find the lowest cost. You can see that is the lowest cost path to S goal, but you saw it kind of like uniformly expanded. Make sense? Okay, so this algorithm is the simplest algorithm, but it's obviously not the right answer. So if you want to do better than best first search, how can we do better?
Include the distance from the goal.
Include the distance from the goal, right? But if you knew the distance from the goal perfectly, then your problem would be solved. So I think the important thing is trading off between domain knowledge and like solving the problem. Okay? And so the idea in A* search is that you should have an F, as they were saying, that should estimate something about the cost of the path to the goal, right? Because you want to like get the shortest path, so you want to be directed towards things that are close to the goal. But it's not going to be perfect. So it's going to be like an approximate guide towards it. And so you're going to introduce the idea of a heuristic, right? So there's a really nice textbook called Heuristics by Julia Berg. But the idea of a heuristic is that it's like an approximate function that kind of tells you which things are closer to the goal and which things are, right? And we'll define it more formally. But a heuristic H is going to tell you for some state S, H of S is some approximate underestimate of the cost of the goal, right? So you can think of it like an optimistic estimate of the cost of the goal. It's always going to be lower than the actual cost of the goal. Yeah. And so the idea is that, so an example of a heuristic is I want to find the distance from here to the exit. I'm just going to draw a straight line from here to the exit. That's a heuristic. Because it's definitely an underestimate of the distance just by triangle inequality. But a heuristic is something that is telling you it's an underestimate of the cost of the shortest path from a particular state as to the goal. If your heuristic was, the optimal cost to go, then your problem would be solved. Okay, so often how do these heuristics come about? They come about through domain knowledge. You use your expertise in the problem to design a heuristic. For those of you doing reinforcement learning, it's a lot like reward shaping. And it's like designing a reward is kind of like designing a heuristic, kind of a similar idea. And what we're going to do with the heuristic is that we're not going to evaluate on G of S anymore. We're going to evaluate on G of S plus H of S, right? And so in the example from before, I'm not going to go in the opposite direction because that's going to have really high H of S. I'm going to go in a direction towards the goal, right? So that's kind of going to direct your search towards. So that's the whole point of the heuristic. It's coming from domain knowledge and it's guiding your search to be a lot closer. Okay, so that's the idea of a heuristic. Some examples are, the minimum number of nodes to go to the goal, Euclidean distance to the goal. So in a path like this, right, you can say, okay, I want to find something that goes from here to here. And so you have, a relaxed path. So this is definitely going to be a shorter path than what I actually have to do, right? But it's going to be an underestimated cost.
I felt like guys were finding like the optimal path, like assume like the weight of the edge is like possible.
Correct. So A* will also find an optimal path. The important thing is that A* will find an optimal path if the heuristic is an underestimate of the cost. So as long as you can guarantee that the heuristic is an underestimate of the cost, A* will return an optimal solution. So I think there's a difference between like the number of node expansions and the path that you find, right? So number of node expansions is like where you explore what things you put in your priority queue. And the optimal path is like, once you've expanded all those nodes, what is the best possible path, right? So both Dijkstra's and A* will find you the optimal solution. A* will find it for you in less node expansions. Because it's more.
So if I'm saying it's fast.
Exactly, much faster.
So that's why you want to use this.
You definitely want to use A*, right? And the important condition we'll talk about next is the heuristic has to be an underestimate of the true cost to go. And like the point is that if it's an overestimate, then you might like discard optimal paths. Like imagine that your heuristic for like a low cost path actually overestimated it, right? Then what's going to happen is you're going to like discard that path even though it is optimal. Right? So as long as it's an underestimate, you're good. But if it's an overestimate, you're no longer optimal. So in general, like the way I think about heuristics is that take your like difficult problem and relax it. And usually the solutions to a relaxed problem are like underestimates of the true cost. So for instance, you want to do like grasping, right? Imagine like grasping usually needs you to get somewhere and like touch something and pick it up. Like imagine you had a heuristic, which is like if I like got to an object and it suction cupped magically into my hand and then I flew away, like that is a relaxed problem. And so typically, if you want to just like a general recipe for designing heuristics is a solution to a relaxed problem, right? Or like imagine that you're in an obstacle world, like disappear half the obstacles. Relaxed problem, right? And it's an easier problem to solve than the actual problem, but it's still going to like direct your search. So it's like often a balance between how much domain knowledge you want to put versus how efficient things are. Does that make sense? Okay. So this A-star search actually came out of this program at Stanford called the Shaky robot, which is a big thing. I might have talked about it at the start of lecture, but yeah, the search algorithm actually came out of like trying to do path planning and navigation of the robot at Stanford. And so the idea of A-star is just the same as best first search, except your priority queue, F is now going to be G of S plus H of S. So it's going to be your cost to come plus your heuristic H of S, right? And both are going to find the optimal path as long as H is an underestimate, but A star only expands relevance. Okay, so you can see from the curve even here that uniform cost search or Dijkstra is kind of like going everywhere, whereas A star is like a lot more directed right towards the goal. And so less node expansion, it means faster. Okay, so let's run through an example of A star search on an actual graph, right? And looking at the pseudocode and see if we can understand what's happening, right? So just run through the pseudocode while you haven't expanded the goal, remove the S to the smallest G of S plus H of S from the open, insert it into closed. For every successor that's not enclosed, you want to check if the minimum cost through that edge is lower. If so, you update the table, insert S prime into open, and repeat. So everything else is the same from the from Dijkstra. You just have replaced F with G plus H instead of just G. Okay, so let's go through an example, right? So we're going to start by just having S start in the open queue. You're then going to like so important to look at. So this is the eight values are given here. Right? The heuristic is 3 and 2 and 1 and 0 and 1, right? And importantly, like you can see that H is an underestimate of the cost to go. Like the cost to go from here is 1 plus 2 plus 2, right? To 5, but H is an underestimate. Here's an underestimate. Everywhere is an underestimate. Right? And so you start with S start. There's only one thing to expand, so you add in S2 now into the thing. Only one thing to expand. Now you add in S1 and S4. Now S1 has G equal to 3, H equal to 1. S4 has G equal to 2, H equal to 2, right? So these are like equal, G and H are equal, right? And so it kind of doesn't matter. You just expand any one of them. So you expand S1, and now you have G equal to 5, H equal to 0, and G equal to 2, H equal to 2. So this one is more promising. So you're going to expand S4. You're going to add in S3. Now you're going to have G equal to 5, 1 plus 1 plus 3, and H equal to 1. So this is going to be 6. This is going to be 5. We'll expand total beta. And so this graph is maybe not the clearest in why it's more directed, but the point is that heuristic will eliminate things that are like definitely not close to the goal, even if they're close to the start. And so you want to have G plus H because G is what is close to the start, and H is what is close to. Right? Okay. So that's just the general idea of A-star search. You have these heuristics that we talked about. There's two properties we really care about, right? So one property is admissibility. Admissibility says that H of S is less than or equal to H star of S. Determine the what?
The heuristic.
Yeah. So it's usually either you solve a relaxed problem or you use domain knowledge. Like you want to like usually it's up to the like application designer to design this. So it's not like it's a one size fits all. There's like it's a bit of an art designing this. But it just has to be understood. So the two conditions you need on your heuristic when you're designing it are that is admissible, which means that h of s is less than or equal to h star of s, right? And that h of goal is equal to 0. And that it's consistent, right? So if you have an admissible just means it's an underestimate. And consistent means that it's an underestimated every substep of your path, right? So it's saying that like h of s is less than or equal to the cost between any s prime that is a neighbor for it and h of s prime, right? So every heuristic that is consistent, so you can think of consistency as like one step admissibility, right? And so everything that is consistent is admissible, but not everything that is admissible has to be consistent. So as long as you have something that's admissible, you will get something that is optimal. But if you have something that is consistent, you won't re-expand those, right? So there's a difference between a heuristic that is admissible and a heuristic that is admissible and consistent is that admissibility will eventually get you to the solution, but you might have to re-expand nodes. Like something will go on the queue, will come off the queue, will go back on the queue, so you might have to re-expand nodes. But if it's consistent, it basically will never re-expand. But it's a harder condition to satisfy. And so when you're choosing these heuristics, you definitely want to be admissible. Consistency is nice to have, not as important, right? And the intuitive way to think about it is admissibility just means underestimation. And consistency means like underestimation every step of the path. Okay. So all heuristics that are admissible are consistent. Not all heuristics that are consistent. All heuristics that are consistent are admissible. Not all heuristics that are admissible are consistent. Yeah. Okay. So the main point to take away is heuristic design is a bit of an art. There's a huge textbook on how to do it for lots of different problems. The way I like to think about it is take your complicated problem, relax it, find a solution to the relaxed problem. That's often a good heuristic. And they give us an optimal solution. So you still get the optimal path, but you do it with much less node expansion. Right? Yes. So the traffic is going to make things harder, right? So a heuristic is imagine that you did it with no traffic. Like, so a heuristic would be compute the path with no traffic, right? And that is going to be definitely an underestimate of your goal, or compute your path as the bird flies, right? Like just go, no, you don't have to follow the streets or the highways or anything, just like take the diagonal path to the goal. Well, the distance, I guess my point is a heuristic is imagine that you had to go, this is like, Seattle and this is like Portland, right? Like you have to go through these set of paths to get there. Like a valid heuristic is like that distance, right? Or a valid, and like say like these things had like some amount of traffic on them. Like a valid heuristic is something that assumes there's zero traffic. So you're like going at max speed 12, right? And so the point is that those will always be underestimates. As long as underestimate is fine. Now there's like useless heuristics, like h equal to 0 is an underestimate, but it's a useless heuristic, right? So there's like some balance between heuristics that are meaningful and like heuristics that are too hard to compute. Right? Like if I had to set h of s to h star of s, right? Then I like have to solve my whole problem. Like then I have to compute the optimal distance. That's a hard problem, right? So you want to have some balance between things that are, underestimates and easy to compute and things that are useless. Okay. So let's talk a little more about heuristics, right? So for instance, for something like grid-based navigation, right? You want to like navigate around obstacles to get somewhere. Heuristics could look something like this, right? You could have something like the Euclidean distance, which is just x squared, or x1 minus x2 the whole square plus y1 minus y2 the whole square square root, right? Or you know something like a Manhattan distance, which is you just go along the roads, right? So go along x and y, and so on, right? Like you can have basically anything that relaxes you can think of all of those as relaxing your problem, right? Like Euclidean distance is saying there's no obstacles in your world, and you don't have to follow the paths of the lattice. You can just go straight through. Manhattan distance is saying there are no obstacles, but you still have to go along the path of the road. But they're all easier problems than your actual motion planning problem, right? And so That's how heuristic looks for this kind of problem. For something like 3D navigation, right? Often an easy thing to do is to like ignore the theta and just do navigation as if it was 2D navigation, right? So imagine that you had a car which was facing this way, right? And you had to get it facing this way. Like a heuristic would be to like just pretend that you can teleport, right? Because you do have to change the angle. Or if you had like a Dubin's car which has to follow these paths or whatever, like a heuristic is to compute the distance as if you were teleporting, right? Because that's going to be a shorter distance. And so all of those are just underestimates of a like three-dimensional navigation. Yep. Okay, and I'll let you come up with things for arm planning in 3D. There's an endless list of things you could do, but that's the general idea of heuristics. We kind of follow that. So it's an unsatisfying thing because you have to come up with it domain by domain, and you'll try to come up with heuristics in your homework. But in practice, like most practitioners will know something about triggering. And you use that knowledge and code it into heuristic, and it allows you to like make your search way faster. Okay. So now I told you that we want these heuristics to be admissible and we want them to be consistent, right? And the theory says that if things are admissible, then you'll always get the optimal path. And if they're admissible and consistent, then you get an optimal path without any node reopening. So it's optimal and efficient. But I guess the question is, do you always want admissibility? Right? So for instance, if you look between left and right, the admissible one is going to find you the optimal path eventually, but it's like a lot slower to get there than something that is inadmissible, right? And so the point is that there's a trade-off between optimality and speed, right? So for instance, admissible will guarantee that you get to the optimal solution, but inadmissible will get you a solution that's like kind of good, but faster, okay? And so oftentimes you want to make this trade-off. And so you don't care about getting the shortest path. Often you just care about getting a path. Right? And so really you have this trade-off between solution quality, which is saying, is my path the shortest path? And the number of states expanded, which is saying, how many different nodes did I expand to find said shortest path? Right? So you often want to just trade these things off. And so there's like a natural thing we can think about, which is this idea of weighted A star. And so A star search is saying you want to expand nodes according to G plus H, where G is cost to come, H is cost, H is the heuristic, right? You're going to put things into your priority queue and expand according to G plus H. What weighted A star does is it says open according to G plus epsilon H, where epsilon is greater than 1, right? So it's saying bias towards states that are closer to the goal. Now, if epsilon is greater than 1, let's say epsilon is 100, right? Then G plus epsilon H is like, you can almost think of this as a new heuristic. It's a new heuristic where it's like a scale 100 times, right? Now, that is definitely not admissible. Like, imagine your heuristic was always like 1 less than your optimal cost, and now you multiply the heuristic by 100. Like, it's definitely not admissible, right? So you no longer have guarantees of optimality, but you will often find the solution a lot quicker. You'll find a worse solution more quickly. Right? That's the trade-off. So let's kind of look at this schematically. So if you have a start and a goal, uniform cost search or Dijkstra often expands uniformly in all directions, so it has no notion of how to get to the goal. Right? So it looks something like this. Now, if you have like A star search, it often expands something like this. So it has some notion of how to get to the goal, but it wants to find things that are optimal, right? And so it does something like this that finds an optimal path, but often it takes like too much memory. So you're expanding too many nodes, too many things in a priority queue, you run out of memory. So what weighted A star search does is it looks something like this, right? So it starts from your start, and you'll see that the solution is suboptimal, right? So the solution it's going to find is suboptimal. Like it goes this way, it goes this way, it goes this way. It's a suboptimal solution, but it found that with way less things in memory, right? Because you're like biasing your solution more towards things that are closer to the goal. Sometimes that's going to lead to suboptimality. And then the trick is finding the bias that leads to something that's not so suboptimal. Right? Okay, so the only difference, so let's just back up. We have best first search. First instance here, best first search is priority of the nodes is cost to come. That's like stress. Second is A star, where it's cost to come plus heuristic, right? So cost to the node plus estimate of cost to the node, A star. And the third is weighted A star, where you upweight the heuristic. And so you're going to get solutions that are a little bit suboptimal, but you're going to get them faster with less memory usage. Are you following me? Okay, so that's the idea of weighted A star, right? And so you can see that, with epsilon equal to 1, you find an optimal solution. And as you increase epsilon, you'll often find suboptimal solutions, but they're often good enough. Right? And so in practice, in most practical problems, you just want to find solutions that are good. If you apply this to something like a robot arm, let's see, will this video play? It looks something like this. So you can actually apply it to problems in practice. So motion planning with the robot arm looks something like this. And it's difficult because it has like 20 degrees of freedom on it. And then you can apply it to like real life systems like quadrupeds and so on. And so here you have like heuristics which ignore the like legs and pretend that the body is floating around, right? So again, it's like you can think of the heuristics as kind of like a relaxed problem. Imagine that you didn't have to obey the physics of the legs and you could just like fly through the air. That's the heuristic that you can use. So yeah, this is from several years ago, but it seems to work reasonably well for a pretty complicated system. No Boston Dynamics, but it's good. Okay, so that's the idea of heuristics and A star search. Any questions? We covered a lot, so I'm happy to pause here and take any questions. So I guess the question for you is, when might it be bad to use a heuristic? Like, is there ever a case where it's bad to use a heuristic, or should we always? Yep. If there's a lot, yeah. So if there's a lot of obstacles, then you use like a silly heuristic, like fly through the air. That heuristic is almost useless. And so, yeah, in those cases, it might be bad. So that's definitely one. You can also have completely uninformative heuristics, like h equal to 0 is an uninformative heuristic, right? You can have heuristics that reorder the, like, you can have like heuristics that reorder the states, even if they're underestimates. Let's say like you had underestimates that were reordered. So like cost A was 5 and cost B was 7, but the heuristics are like 3 and 1, right? So they're reordered, and that you'll still find the optimal path eventually, but it's gonna cause unnecessary node expansion. Right? And so there's problems like that. It's often like choosing the heuristics can be hard. The other thing is choosing the heuristics can be computationally expensive. So you want to choose a heuristic that's computationally cheap, but still important. Okay. And then the last thing we want to think about is this idea of lazy A star, right? So we've talked about everything in terms of like the node expansions, right? So we said, okay, we don't want to expand as many nodes as possible. We want to be as close to the target. But really, is that the most expensive step in motion planning, right? And the answer is that edge evaluation is actually really expensive, right? So in a graph search problem, you often want to, like, the thing that is most expensive is not just like edge. It's not just the number of nodes that you expand. It's like checking for collision is actually really expensive, like because you have to use a simulator, you have to simulate a number of different steps, and so oftentimes you want to not just minimize the number of node expansions, but you want to minimize the number of edge evaluations, right? And so what lazy A star, all it tries to do is it tries to minimize the number of edges that you evaluate, right? And so the intuition here is that in most planning problems, like the lines here are trying to show the proportion of time that is edge evaluation versus other things, you can see that most of planning problems, like essentially 100%, is covered by edge evaluation. And so really we want to minimize the amount of edge evaluation. And the idea of lazy search is not so much to minimize the number of node expansions, but the number of edge evaluations. Right. So if I'm trying to check if A and B have a collision-free path between them, like that is the expensive part, right? Not just like expanding another node. So let's kind of see if we can instantiate this. Right. So we have best first search with this particular graph. Let's say you so the way you're going to do A star search is that every time you expand for a successor, right, you check if it's in collision or not. Right? So I'm at S, I took out S, I added in A, I added in C to my priority, and every time I added, I check if the edges are in collision or not. Now, the problem is if C is never going to be used, right? If C is like not really useful, then why am I wasting my time collision checking on C? Right? And so the current version of A star we've described checks for edge collisions when you put things into the priority queue. So you put A and C into the priority queue. When you do it, you check if S and A have a collision-free path and S and C have a collision-free path. And that's you're wasting time on C if C is not relevant, right? And so let's not waste that collision check. And so the idea of lazy search is procrastinate as much as possible to do edge evaluation, right? So like only evaluate C if it's like really going to be useful to an optimal path, right? So it's like don't evaluate C until you really have to. Or don't evaluate the edge between S and C until you really have to. Yeah. So let's try to look at the key ideas behind lazy A star search. So when you're expanding a node, don't collision check edges to successor, right? So you're at S, you added A, you added C. Don't collision check at that point. Add them into your node. And into your priority queue with where they came from, right? So say add in the edge SA to the priority queue, add in the edge SC to your priority queue. Yeah. And only when you're expanding a node, collision check the edge to the pair. Right. So if you go back to our example from before, like basically when you add things to the priority queue, don't collision check here and here. Only when you expand, let's say you're expanding A, that's when you collision check to your parent, right? And the reason is that if C was like not useful, then it would never be expanded. So I don't waste the collision check. And so the idea of lazy A star is just to when you're expanding a node, only then you collision check. So you only collision check paths that are likely to be good. The only difference now is that because you're not collision checking to start, you might have multiple copies of a node, each with different pairs, right? In your queue. And so you might have to deal with that when you're doing search. Right. So then if lazy A star, just do A star, but don't collision check when you're opening nodes, or don't collision check when you're adding nodes in, which are successors. Only collision check when you're expanding. So when you're expanding a node means it is the most promising thing in the priority queue. Only then you collision check. Okay? And in doing so, you only collision check optimistic, like good things. Right. So let's kind of look at the differences between the pseudocode. Right. So the non-lazy A star is saying remove S with the smallest thing for every successor, right? For every successor S prime, check if it's in collision. If it's in collision, set C to infinity, right? And if it's not in collision, blah, blah, blah. What we're going to do in lazy A star is you're not going to do any collision checking when you expand the successor. You're only going to do collision checking when you expand it. Right, that's the main difference. Okay. We'll skip the example for now, but it's in my slides. You can run through it. But essentially, all it says is that you skip the nodes that are unnecessary. So, for instance, over here, if you had a state with a bunch of successors that are not going to be useful, like normal A star will still collision check all of them, where lazy A star will only collision check the ones that are promising. All right, that's it. Feel free.